Hello and welcome to another Zosin session. How about that? So today we're gonna continue working on this Wang tile project. We've been working for quite some time, and you can find the source code of this project in the description if you're watching on YouTube, or in the chat if you're watching on Twitch. Right, if you're watching on Twitch and you don't know what kind of YouTube stuff I'm talking about, you can find the link to the YouTube channel in here, right? So and we've been developing this thing for quite some time, I think almost a week. So there's this playlist that contains almost all of the recordings of me developing this stuff. So far, how many episodes of Wang tile project we have? We have only 5 episodes, so this is the 6th one. We're developing this thing for almost a week. This is almost a week project, and that's my face after working for 6 days on this shit. So that's basically me after 6 days of that shit. So on the previous stream, we implemented the live visualization, the live rendering of the Wang tiles, right? So by the way, if you don't know what is a Wang tiles, they usually look like this. Look at that. This is a pattern generated using Wang tiles, right? So we have actually 2 patterns right now. So here is the second pattern, also generated a Wang tiles technique, right? So, and what is a Wang tiles? Basically, Wang tiles are square tiles. Each side of the tile has 2 or maybe more colors. In our case, we are considering only 2 colored Wang tiles for the simplicity. Right, so, and because you have 4 sides and 2 colors, you basically have 2 to the power of 4 tiles, right? So if you want to have all of the combinations of colors, you need to have 16 of such tiles. So what do? We have a simple function that takes the description of the tile as a bit mask and the coordinate on the tile, on the texture of the tile, and produces the pixel, the color pixel. We take that function, and the first thing we do, we generate an atlas, which is this full set of the Wang tiles, right? So we generate all of the possible Wang tiles, all of the 16 of them. Then we're generating the Wang tile grid. And the thing about Wang tile grid is that each tile in that grid has to comply with the constraints of the colors. So basically, you can only place a tile adjacent to each other if they have the same color on the corresponding sides, like a domino game, right? In a domino game, you can place the dominoes only when they have the same values. This is the same situation. You can only place the tiles when they have the same colors on their corresponding sides, right? So, and then we generate a huge tile grid, and we just randomly placing these tiles, maintaining the constraints, and that's the patterns we get. So we're basically generating a tile patterns just from a single function that generates pixel on the texture of the tile. That's the goal of today's of this project, and we kind of already achieved the goal, right? So you can just run this entire thing, and it will generate you the atlas, which is all of the possible combination of the tiles. I should probably put the black background so it doesn't screw up the encoding, and also it generates the grid. So as you can see, here it is. But it does that in a batch mode, right? So you just run the program once and it generates 2 PNGs, the Atlas PNG and Grid PNG. And what we did on the previous stream, we actually animated that grid in real life. So we took our engine for rendering Wang tiles and we hooked it up into X11, right? And this is what we come up with, right? So this is basically our engine rendering the tile grid live, right? And we're animating these things and changing some stuff and so on and so forth. So yeah, that's basically what we did on the previous stream, and I suppose I could give you the link to the previous stream, but you can find it in the playlist that I put in the description, right? So, but that one is X11 app in C with Xlib. So if you're interested in this thing, let me remove unnecessary crap from the URL. All right, so, and I'm gonna give you that link in the chat and also in the description in case you're watching it on YouTube. So, previous episode about X11 development. So that thing was actually super fun. I really enjoyed working with X11, with Bev X11. So, and what we're going to do today? Well, I wanted to do today a little bit of a maintenance work, but I hope it's going to be a little bit interesting. Okay, so how do we manage the memory for our renderer? Believe it or not, I didn't expect this project to grow so big, even though it's 500 lines of code. It's not that big, but still, it's becoming more and more complex. So what I did essentially, I just allocated a bunch of arrays in a global scope, right? So here's the memory for the atlas, where we store the pixels of the atlas. Here's the memory for the grid itself, and here's the memory for the grid in pixels, which generates an actual image. And we basically have a bunch of functions that just write pixels into these regions of memory. So since these regions of memory are static, well, they're not technically static, but we can make it static, it's impossible to resize those regions at the runtime. You can only resize them at compile time by modifying one of the compilation parameters, right? Like this one. Right, so which is not particularly convenient, and one of the things I wanted to have in my application is an ability to actually say, okay, I want the tile to be 64 by 64 and grid, let's say, to be 100 by 100. And what I want this system to do is to take these sizes, calculate how much memory it needs, and allocate that memory dynamically, not statically. Right, so, and with the current system where we just literally have the memory hard-coded in a static memory, it's not particularly possible. So this is basically what I want you to do today. I want you to go through the code base and just change the static memory into a dynamic one. And here is an interesting thing. So the cool thing about this static memory is that the whole memory is located continuously, right, in a single chunk. I actually lost my memory, wait a second. So yeah, there we go. So what I want to do, how I want to manage my memory. So I want to grab the dimensions that the user wants. Right, I want to grab the dimension the user wants, calculate the final size of the memory chunk we need, basically including all of these things, and make a single allocation. Right, I want to do a single allocation, and then I get the huge region of memory, right, I get a huge region of memory, and I subdivide that region of memory for Atlas, the grid in tiles, the grid in pixels, and I basically write into these subregions of the single allocation. The reason why I want to do that, is because managing such memory is going to be extremely easy. Deallocating and basically deinitializing the whole renderer is going to be just a single free. So you allocate memory once, only once, because you know precisely how much memory you need. You can just allocate it once, and you can deallocate it with a single call, just scrapping everything. That makes it way faster than, you know, making a lot of small allocations, right? You actually, if you want to go fast, by the way, the rule of thumb, not necessarily always, but the rule of thumb is to make as little allocations as possible. Just figure out how much memory you need up front, allocate that memory, and subdivide that memory accordingly. Right, so it will make it faster, first of all, and second of all, it will make it simpler. Right, it will make it way simpler, because again, allocating is just one malloc, and deallocating everything is just one free. So, and the simpler the program, the less bug you're gonna have, right? So we should all strive for simplicity. So the simpler the code, the easier it is to find bugs and problems. And that doesn't make sense. Doesn't make sense. I hope it makes sense. I don't know. So the code here, the algorithms in here are actually pretty complicated on their own, so we're gonna have bugs, of course, but hopefully those bugs are not gonna be caused by a complex memory management system, at least. So you're gonna be, so they're gonna be caused by other complexities that are necessary. Right, so you're always going to have some sort of complexity, right? And that complexity is always going to cause bugs. You just want to make sure that you don't have unnecessary complexity, because once you have unnecessary complexity, you start to have unnecessary bugs. You only want to have bugs that are necessary. Right, you don't want unnecessary bugs, right? Only necessary ones, please. Bugless. Well, it's never going to be bugless, of course. I would argue that applications without bugs don't exist at all. By the definition of bug. So the definition, the useful definition of a bug actually kind of implies that you can't write bugless applications. So, all right. So let's go ahead and do that, I suppose, right? So let's go ahead and do that. What do you guys think? Sounds good, sounds Gucci, sounds a Tamaguchi. Whoa. So I put static in here, so I don't think I need anything in here. So let's create a branch called dynamic, right? So this is going to be a dynamic memory. And the first thing I want to do probably is to maybe add a bunch of flags to control the size of the tile and the grid. Maybe I don't even have to do that right now. Maybe I can just have like a runtime parameters, right? Tile width in pixels and tile height in pixels, right? So, and initially they could be equal to some sort of a default value, right? And the default value could be this. I could simply rename this thing to default, right? I could rename it to default and then just basically assign default tile width in pixels, right? Default tile width in pixels and default tile height in pixels. But I don't want to remove these constants yet right away because there is enough code that kind of depends on these constants, and removing them right now will introduce too many compilation errors that I don't really want to follow. Right, so I'm gonna just create the necessary things, and things are that needs to be removed later. I'm gonna remove them later. So we're gonna refactor the code incrementally. Make sense? Okay, so basically I want to be able to only provide two parameters, right? The size of the tile and size of the grid. The size of the grid in pixels is basically size of the grid in tiles multiplied by the size of the tile in pixels, so it could be calculated based on these two parameters. So there's nothing particularly needs to be done in here. Yeah, there's nothing particularly needs to be done in here. So I'm going to only provide something like grid width in tiles, right? Which is also going to be equal to default grid width in tiles. There we go. And this one is going to be height, right? So there we go. So here are compile time parameters. And as you can see, yeah, so the grid width in pixels is usually computed by taking the value in tiles and multiplying by the tile size in pixels, right? So we have several measure units in here, which are pretty important to not confuse, right? So it's quite important. Let's put a default in here, right? So here is the default. And let me see, did I put this thing in here? Okay, so here are the parameters. Okay, so one of the things I probably want to do, I want to take all of that memory, so atlas, what is that? Yeah. And put it probably into some sort of a structure, right? I want to have the pointers to the memory regions and the sizes of those memory regions to be in some sort of a structure where you can access all of them when you need to perform some sort of a rendering. The question is, how should we call such structure? I guess the best way to call such structure would be renderer, right? So it should be some sort of a renderer, right? So it's going to be type def struct renderer. There we go. So, and it's going to contain the atlas, the grid in tiles, and the grid in pixels, and all of the size in here. So one of the important things it's going to contain is the tile width in pixels and tile width and height. So this kind of thing should be provided by the user, right? So user have to define tile width and tile height, and then we need some sort of a function that will grab these values and allocate memory accordingly. So I would say that this thing is provided by the user, right? This thing is provided by the user, and this thing is also provided by the user. Okay. So next thing is what? We have the atlas. Let's put the atlas in there. So it's going to be RGBA32. Pointer to the atlas region, right? Pointer to the atlas region, and we also need to have these parameters in here, right? So atlas width in pixels. So it's going to be size t, atlas width in pixels. Right, and another one is atlas height in pixels. So, and essentially, it must be always equal, to atlas width in tiles. So atlas width in tiles, I don't think it makes sense to let the user even customize this thing, because the atlas is going to be always 4x4 in tiles. Right, so there's no reason for the user to even customize that. It's something that is baked into the application. So this entire thing is going to be has to be always equal to atlas width in tiles multiplied by tiles width in pixels, right? And this thing is provided by the user, so that means the process of initialization should take the size of the tile, multiplied it by the size of the atlas in tiles, and assign this value in here so we don't recalculate it all the time. Right, so, and the other thing must be something like atlas height in tiles and then tile height in pixels. There we go. So we have something like this. So, and this is basically the dimensions of the atlas itself, right? So it's the dimensions of the atlas itself, and you will use these values to access the pixels within that memory region, because, yeah, it's sort of like a two-dimensional array, but it's kind of difficult to refer to the two-dimensional arrays in C dynamically. You can do that, but you have to know the size of the row, right? So, yeah, and of course you can have a pointer to pointer, which is even worse, because in that case it implies that rows are scattered across the memory, and you don't really want your rows to be scattered across the memory. You want them to be continuous in the memory, so it's better for cache locality. So you're kind of forced to like have a pointer to the beginning of the whole buffer and do all of the, you know, shape calculations of the two-dimensional array yourself all the time. Essentially, it is usually like, you know, you have a row multiplied by the size of the row, which is the amount of columns, plus x. You kind of like in C, you have no choice but do this kind of stuff all the time yourself. You know what I'm talking about? Right, so you really don't have any choice. Well, you have choices in some particular situations when you know the sum of the dimensions, like one or another at compile time. But if you know nothing at runtime, yeah, you have to calculate everything yourself. So I'm sorry, buddy. Yeah, it is what it is. C is a very annoying language. Deep Singularity subscribed for 5 months of a tier 1 subscription. Thank you, thank you, thank you. And welcome to our epic two-dimensional array club. Isn't that amazing? Isn't that amazing? I think it's freaking amazing. Okay, so this is only the first one. So essentially what we did, we took this thing and turned it into a dynamic thing. There we go. So this is basically that. So, and we need to repeat that for this thing as well, right? So we have a grid in tiles, right? And it's going to be BLTR. And we're going to have a pointer to this thing. And then we're gonna have the dimensions of that thing. So it's gonna be width TL and height TL. So this is one of the things that is provided by the user as well, right? So the user can provide the size of the tile in pixels and the size of the grid in tiles, right? So this thing is also provided by the user, right? Provided by the user. Emacs doesn't want to autocomplete everything properly. Okay, and there is a last one, grid but in pixels, right? So this is a grid but in pixels, and we're gonna have RGBA32, grid px, right? So size t grid width px, grid width px, and this thing must be equal to grid width TL, which is provided by the user, multiplied by grid by tile width px, which is also provided by the user, right? So we're basically pre-calculating these sizes up front. And a similar thing is going to be for the height as well. Width, replace it with height. There we go. So I guess we did everything in here, so we don't need this thing. And this is what we'll have to pass around all the time to all of the functions that want to render something, right? So, and this structure will contain all of the necessary information about the regions of memory, about the sizes of those regions of memory, where they go, and stuff like that. So, as I already mentioned, I want to only allocate one chunk of memory that can contain all of these regions and subdivide this chunk of memory into 3 regions. So to effectively manage all of that, we need to keep track at the beginning, of the beginning of that memory, right? So I'm going to keep the pointer to the beginning of the memory of the renderer in the renderer itself. So we're going to have something like memory, right? So, and for the cases when we're going to be using special allocators that require you to provide the size when you deallocate the memory, I think it also makes sense to, provide the memory size. So for instance, if we decide to use directly a map to allocate the memory, right? What if we just calculate how much memory we need and we just map that memory, right? To unmap that memory, we also need to know the size of that memory to just unmap it, right? And I think because of that, it makes sense to also keep it like that. I also plan to port it to different platforms and stuff like that, and on different platforms, maybe memory management could be different. So yeah, that's basically the whole structure that I want to have. Do I need anything else? Maybe. Oh, and it's actually kind of important to mention that all of these pointers, this pointer, this pointer, and this pointer, they should point to a memory within this region. So this thing defines a region. So here is the beginning. So here is the size, right? So that means the beginning of that region is memory. The end of that region is the memory plus memory size. So all of these pointers, maybe I can toggle truncate lines. Right, so all of these pointers, right, they should point to a memory within this region. Does it make sense? Right, so maybe I can actually draw that to visualize and stuff like that. So we're going to be allocating a huge region of memory, right? So a huge one. So, and memory, this thing is going to be pointing at the beginning of that region of memory. So, and then at the end of the thing, we're going to have memory plus memory size plus memory size. There we go. So then for the atlas, for instance, it doesn't really matter if it's atlas or something else, but since we put atlas at the beginning, so the atlas is going to point at here. So the atlas will start at here. So, and it will go for some time in the memory, and there you go. So this is the atlas. Then we're gonna allocate the next chunk for the grid TL. So this is gonna be grid TL. And the grid TL also will go in the memory for quite some time, like this. And then this thing will go to grid pixels. Grid px, and it will fill up the rest of the memory. So this is basically going to be the layout of the renderer memory. Right, and this is basically what we keep track of, right? So we keep track of the memory where all of that begins, and then we know where Atlas starts, where now we know where the grid TL starts, and also grid PX, right? And this is how it's going to look like in the memory. So, and what's cool is that if you want to just deallocate the whole thing at once, you grab this pointer and you just call free on it, and that's it. And all of the memory that you allocated for all of these subregions and stuff like that, it's gone. You don't have to worry about it anymore. You see? So that's basically what we're doing in here. Does it make sense? That's the plan, at least for today. To make it like that. And what's interesting is that the memory layout is really close to what we had when we're actually storing that in the static memory, right? Because in static memory we just sequentially allocated a bunch of things, and this is how they were stored in static memory. So it's going to be very close to what we had, only dynamic. Does it make sense? Sounds good? Sounds Gucci? Sounds Tamaguchi? Maybe anyone have any questions about this thing? Just in case, maybe it's unclear. All right. So how are we going to be initializing this entire structure? Well, initializing this entire structure is kind of a pain in the ass, I would say. So some of these things are user-defined. Some of them depend on user-defined, some of them don't, and so on and so forth. So I also need to mention that it should be, this must be within the memory region defined by memory and memory size, right? So, and that's basically what we want to have in here, right? So, and that is true for all of these things, right? So the beginning of the renderer memory, the size of the whole renderer memory. There we go, the size of the whole renderer memory. So let me think how we're going to be initializing all that. I suppose I want to have a function that basically allocates the renderer. So we're going to have renderer alloc, and what it's going to do is going to accept the pointer to the renderer, right, and the user-defined parameters. Because you see, it's kind of difficult to properly enforce, you know, correct initialization of the structure, right? So we could basically say, okay, so you are allowed to set these parameters, but not set these because they're going to be set by somebody else. No, let's actually have a function that accepts the pointer to the structure and also all of the user-provided parameters, all of the parameters that the user have to define. So it has to be width px, size t, tile, height px. Right, and this function is going to set the user-provided parameters and then the rest of the parameters that depend on the user-provided parameters, right? I think that makes sense, right? So size t, grid width tl, size t, grid height tl. There we go. So, and then it's going to allocate all of the memory and stuff like that. So what's interesting is that, what if the user tried to call this thing like twice? What if the user tried to call this thing twice? So we probably could assert that this thing has to be equal to null, otherwise you won't be able to allocate it or something. Or maybe we could completely change the approach we initialize the renderer. Right, so let's actually create, you know, the function that frees all of the memory, right? So this is going to be the renderer, it accepts only the pointer to the renderer, right? So, and it's only going to work if you already have something allocated. So if you have a memory, right, if you have a memory, we're going to free that memory, Right, and once we freed that memory, all of these pointers became invalid. So we need to maybe zero initialize the whole thing to sort of like indicate that you can allocate it again. Right, so it's going to be R, fill it with 0, and how many bytes you want to fill with 0? You want to fill the size of the structure. So this entire thing deallocates the whole renderer. You see what I was talking about when I said that this approach is going to be simple? Right, so this is the whole memory deallocation, right? So you're done with your renderer, you just deallocate it and you just set everything to 0. You don't have to worry about it. Right, so yeah, you don't have to go through this individual thing. And if you add more things in here, you never have to modify this function, right? If you have more regions, this function will just work without modification. If you just, you know, subdivide this entire thing. Okay, so, and in here, you know, I have an idea. What if we call this thing not alloc, but realloc, and we can allow the user to call this thing several times. So essentially, if right, before trying to do anything, we're gonna free this renderer, right? If the renderer had any memory, it's gonna be deallocated and everything is gonna be set to 0. So here we are 100% sure, we're 100% sure that the memory is equal to null. And now we can start populating it again. So basically that allows you not only not to worry about calling it several times, but it also allows you to resize your renderer. You see? So at the runtime, if you at some point you decide, okay, I want to have a renderer of a different size, well, let's just like call realloc with a different size, and it's going to basically free everything and allocate a different chunk of memory. Right, so yeah, that's the idea here. So I think that's a relatively good way of managing this entire stuff. So let's go and implement that. Let's go. So realloc. So what we're gonna start with, again, I guess we're gonna start with just initializing these two fields. We don't know the size of the memory yet, so I'm not gonna even bother. Ragul, I hope I'm pronouncing nickname correctly. Thank you so much for gifting a tier 1 sub to Pretzel Rocks. Okay, thank you so much for gifting a sub, supporting the channel. And Pretzel Rocks, welcome to our epic C development club. How about that? How about that? Isn't that epic? I think it's goddamn freaking epic. Alright, so let's start with initializing everything. I think I want to split my screen in two and just look at the things we're trying to initialize. So this is going to be the first thing we want to initialize in here. So tile width px and tile width px. So we set the tile width and we're going to have a height in here. So there we go. We initialize the tiles. The next thing we need to initialize is the atlas, right? So as we already said in the comment in here, the atlas sizes should be equal to these parameters. So this is precisely what we're going to set in here. So atlas width px is going to be equal to atlas width tl, which is the compile time parameter, and it's fixed and you're not allowed to modify it. And we're going to multiply it by tile width px. All right. So, and then we're gonna initialize height equal to atlas height TL multiplied by tile height px. There we go. So after that, we have enough information to actually calculate the size of the region for the atlas. Right, so, and it's quite important because it's going to contribute to the whole memory size in the future. So the atlas, let's put it like this, atlas size is basically equal to width multiplied by height. But we need to know the size of the atlas in bytes. This is size of the atlas in pixels. So the size of the atlas in bytes is going to be size of a single pixel, which is RGBA 32. There we go. So now we know the size of the atlas region in bytes. Cool. So we kind of initialize the atlas. We're not going to set atlas pointer to anything yet because we don't have any memory. And the reason we don't have any memory because we don't know how much memory we need yet. So we're basically estimating. Right now we're in the middle of estimating how much memory we will need. Right, so let's continue. So we're done with the atlas, let's go back to the grid. And these parameters are provided by the user, right? So they are provided by the user here, so we're gonna just reassign them. So let's go over grid width px is going to be equal to grid width px, and then I'm going to query replace width with just height. There we go, and now I have enough information to calculate the size of this entire thing. So it's going to be grid px size in bytes. It's quite important. Maybe I should call it like bytes. And this thing is basically width multiplied by height. But again, this is in tiles, this is in BLTRs, so we need to convert it to bytes. To convert it to bytes, we need to take the size of BLTR. So, and you know, I want everything to be aligned properly, right? I want everything to be aligned properly, and to align everything properly, I want RGBA32 and BLTR to be of the same size. So that way I can just allocate n 32-bit integers, and everything is going to be aligned to 32 bits. And I don't remember how did they define BLTR. It's already 32. Okay, so they are already of the same type, so I basically kind of predicted upfront what I wanted to have in here. Okay, so that's cool. So let's go back, and maybe just to be 100% sure, I can do static assert and say that RGBA32 must be equal to size of BLTR, and the renderer memory management model expects RGBA32 and BLTR to be of the same size. I hope I didn't make any typos. I have a problem with my vision, to be fair. It's slowly declining over time. So, and because of that, I'm starting to make a lot of typos. The renderer memory management model expects RGB32 and BLTR to be of the same size, and this is precisely what we're checking in here. Okay, so we estimated the size of the grid thingy, so a grid TL. Now we need to estimate the size of the grid PX. So grid width PX must be equal to the... Wait a second, did I make a oopsie doopsie? I think I made a oopsie doopsie. I was supposed to be initializing TL, but I was initializing PX. Alright, so let's quickly do query replace. So this is why it is so important to keep track of different measure units, right? Because if you get them wrong, you may have an memory access violation. So let's replace PX with TL, right? So now we're actually initializing the tiles, not the pixels, because we are about to initialize the pixels now, right? So grid width in pixels is actually equal to this thing in tiles multiplied by the tile width in pixels, right? So, and then I'm gonna query replace width with height, right? So there we go. So, and now we need to estimate the size of this thing in bytes as well. So we're gonna take grid width in pixels multiplied by grid height in pixels multiplied by size of RGBA. There we go. So we estimated all of the sizes. So we know that we need this amount of bytes for the atlas, we know we need this amount of bytes for the grid TL, and we know that we need this amount of bytes for grid PX. And that is essentially what we need to set the memory size to, right? So we're going to say that the memory size, the final memory size, is going to be equal to atlas size bytes plus grid TL size bytes plus grid PX size bytes. So this is how many bytes we need for our renderer. And the next thing we need to do, we just need to allocate that specific region of memory. So we're going to be using malloc, and we're going to just say allocate us this much memory. Just go ahead and do that. So, and if you failed, so malloc may fail, right? It may return null. If it fails, we're going to report the error that we couldn't allocate the memory. So let's say error could not allocate the memory for the renderer. There we go. And then we're going to exit with non-zero exit code, because if we couldn't allocate the memory, well, there's nothing for us to do in this application. We might as well just die. Right. Okay, cool. So we estimated the memory, we allocated the memory. The next thing we need to do, we need to go back to these pointers and assign their values to be within this memory. So basically we got the memory, now we need to subdivide that memory. You see? So Atlas starts at the beginning, right? As we already mentioned, Atlas is going to go at the beginning. So I'm going to go ahead and say Atlas starts at the beginning of the memory. There we go. So now we allocated memory for the Atlas. The next thing, we need to allocate memory for the grid TL. Well, it's gonna start from the memory, and now we need to add the size of the tile, right? So let me actually grab this color, right? We need to add the size of the Atlas to get to this position. Right, and we already know the size of the Atlas, so it's basically Atlas size in bytes. But we have to be super careful, right? Memory is void star, and as far as I know, doing memory like pointer arithmetics with void star is not particularly a standard feature. Since we want to do pointer arithmetics in terms of bytes, it would make sense to actually cast the pointer to the char, so all of the pointer arithmetic is going to be in bytes. There we go. So we basically subdivided the region for the grid as well. So the next thing we need to do as well is, you know, add to the grid, right? Add to the grid the size of the grid and find the location for the last region of memory, right? Find the location for the last region of memory. So it's going to be grid px. So in this case, I'm going to take this thing, I'm going to add the Atlas size, and then I'm going to add grid TL size in bytes. And there we go, we initialized all of the pointers. So, and I guess that's the whole initialization. This is the whole function render realloc. Right, we're assigning all of the values, we are calculating all of the sizes, we're estimating how much size, how much memory do we need, and then we just allocate a huge chunk, and then we just subdivide that chunk into the corresponding regions. Does that cast char star make any difference? It does make difference in the sense that this thing is more standard compliant. As far as I know, some compilers allow you to do pointer arithmetics with void star, and the pointer arithmetic with void star is basically the same as with the char star, but it's, as far as I know, it's not a standard thing. Right, according to the standard, you're not really allowed to do this kind of thing, but we can try actually. So let's give it a try. We can remove char star, right, and see what the compiler will tell us. And I think the compiler will tell us something because we are being very pedantic about following the standard, right? So if there's something non-standard, the compiler must tell us, right? So let's give it a try. And the reason why I care about following the standard is because I usually want my applications to be portable, even though like this thing is probably working only on Linux, but it's following the POSIX standard, and the POSIX standard is more portable than you think. So yeah, it still makes sense to care about portability. Okay, so what do we have in here? No semicolon. So I have a bunch of warnings in here that I probably want to fix first. Let's actually go ahead and fix them all. And pointer to void used in arithmetic. Yeah, there we go. Pointer of type void used in arithmetic. And this is a warning that came not from pedantic actually. It came from arith thingy, like pointer arith. There is a specific warning for that. But as you can see, it's not a compilation error. It's just a warning. So to get rid of this warning, I prefer to just, if I mean to do pointer arithmetics on the level of byte, on the resolution of bytes, I prefer to explicitly say that. So it is better for the portability, and it is better for readability as well, because you explicitly tell the human who's reading this code that this is the resolution at which you're doing pointer arithmetics. I think it makes sense, right? It's just like generally makes it more readable. All right, so, and there is another thing, we're assigning incompatible pointers. So after we're done with the pointer arithmetics, I think it makes sense to cast this thing to the corresponding pointer, right? So we're making it even more explicit. So we used character just to find precisely the location in the memory, and then once we found it, we casting it to, we basically reinterpret it to the type that we want. We could probably do all of the pointer arithmetics in 32 bytes, which is not a bad idea. Essentially, we could reinterpret all of these things to uint32, and we could change the sizes to be in pixels. And since we know that RGBA32 and BLTR are the same thing, I think it's gonna work. But I'm just afraid to touch this code, so I'm not gonna do that. Alright, so let's go back to character. So sometimes it's kind of scary to touch this. Look at this thing, it's a spaghetti. Mamma mia. Anyway, so okay, so we have a couple of things in here. Oh, I removed those references, and now the compiler wants me to go through each individual place where we were referring to these arrays and fix them accordingly. So I think I don't want to go that route yet. So I'm gonna bring back the arrays that I removed. So I'm gonna basically discard the removage of these arrays because I just want to check if my thing compiles. Okay. The only warnings we have is unused variables in here. So, okay. This is how I envision the initialization process of the renderer. What do? You take the renderer structure and you allocate it on a stack and zero initialize it. That's it. That's everything you do. Then you go and call renderer alloc, realloc rather, right? So providing the pointer to this thing, and then providing all the user-defined parameters, right? So okay, like this. Boom. And what it will do, it will just initialize everything. And then at the end of the entire stuff, you're gonna do renderer free, and you're gonna just free the entire thing. So that's basically the plan. So you have these parameters, you initialize the renderer will allocate all the memory, and you can just use it. And within the renderer itself, you have all of the necessary information to perform the rendering, right? Pointer to the atlas, grid px, the sizes of all of these things, the sizes of the tile, and so on and so forth. And we're probably going to add more things in here, right? So yep, that's pretty straightforward, I would say. The initialization is quite involved because we just need to estimate how much memory do we need in here. But apart from that, I think it's fine. I think it's fine, and it seems to be compiling. So maybe we could just take a look in the debugger how the process of initialization and allocation is going, right? So let's go. So maybe we can just do something like gut gdb, and can I go to wang? There we go. So, and can we break specifically on here? So it's gonna be gut break. There we go, and let's run the application. Okay, cool. So maybe we want to keep displaying the renderer that we're currently initializing. And I wonder if there is a way to pretty print those things, because I would like them to be like each on separate line, but I'm not sure. JDB pretty print. Does your char mean you can only index up to 255? No, it doesn't mean that. What happens if your tiles are addressed at 25? It doesn't mean that. Char star means that this is a pointer that points at an element of the size of character, right? So yeah. So let's imagine that you have something like this. Here is your memory. And you can have many of them that go there. And imagine that you have a pointer of a char star. So char means the size of the element. Right, so if you do arithmetics with a char star, you jump by 1 byte. Right, you always jump by 1 byte, and that's basically what it means. And you can jump how many times you want. As a matter of fact, basically as many times as the addressing of the architecture allows you to jump. If you have something like maybe, let's say, pointer to uint 32 underscore t, the size of this thing is actually 4 elements. Right, so, and that allows you to jump by 4 elements and so on and so forth. So essentially the type of the pointer just determines how far you can jump when you do +1. So +1 for character means that I'm gonna jump within the memory by 1 byte, but +1 for uint32 means that I will jump by 4. If I had something like uint64, I would jump by 8 bytes. So, and if I had structures that are big, like for example 256 bytes, +1 with the pointer to that structure would mean that I will jump by 256. It has nothing to do with how limited addressing is. It is not limited, it's limited by the architecture. So it defines the step within the memory that you can do. Okay, nice. It's like a stride, almost, I guess. Yeah, not really. Maybe you can think of it as a stride. Yes, you can think of it as a stride. Sure. So that's basically what it means. Debugging with GDB. So how do you do pretty printing? Pretty print arrays. Okay. Cause GDB to print structures in an intended format. Okay, set print pretty on. Okay. Can I just do it like that and just set pretty on? And then if I step, oh, would you look at that? Isn't that amazing? But it doesn't fit entirely into my screen. So that's kind of sad, but anyway. All right, so, yep. So we set the tile width 64. I wonder if I can just split this thing like this, because I want to be able to see everything, seriously. I wish we had a good debugger on Linux. I wish we just had a good debugger, but we just can't have a good debugger. Alright, so here's where we are. And can I do the next step? And there we go. So we initialize tile width and tile height. Okay, so the next thing we're going to be initializing atlas width in pixels, right? So the atlas width is 256 pixels, and then 256. Okay, so the next thing we are initializing is the grid 13 by 10. So this is the default values. That makes sense. And now we're initializing grid width in pixels. So this is the width in pixels, and this is the height in pixels as well. Cool. So the next thing, we're trying to figure out the memory size. So this is how many bytes we need to allocate for the renderer. MCQ8 subscribed for a year with tier 1 subscription. Thank you for a year of subscription, and welcome to our epic memory management club. So this is basically amount of kilobytes, so basically 2.3 megabytes or 2.4 megabytes. That's how much memory our renderer wants. Can we afford 2.4 megabytes in 2021 already? That's a very good question. Is that even affordable in 2021? I don't know. So the silicon shortage actually may mean that we won't be able to afford this amount of memory. So maybe, yeah, my renderer will not be feasible in 5 years. Who knows? We'll see. So, and then we allocated the memory. So here is the beginning of the memory. Cool. So, and after we've done all of that, we're gonna start subdividing things. So we're gonna be going back to these pointers and assigning them back. We assign the pointer to the atlas, we assign the pointer to the grid, and we can even check their sizes, I suppose. You can always just take this pointer and subtract it from that pointer, right? And that's gonna be the size. So this is basically the size of the atlas. Right, so this is the size of the atlas. Well, I mean, it's actually the size of the grid, but anyway. And as far as I can tell, we initialized everything. So this is where the memory starts, this is where Atlas starts, this is where the grid TL starts, this is where grid PX starts, this is their sizes, right? So, and yeah, we have all of the necessary information. So looks very, very good. And then we just return from that and we have a fully initialized renderer. I don't see any particular mistakes in here. Almost fits an L2 cache. What's the size of the L2 cache? L2 cache size. I don't know. I'm not a programmer. L2 cache varies depending on CPU, but its size is basically between 256 and 8 megabytes. Most modern CPUs will pack it. That's pretty cool. What's a good debugger? I've only used Visual Studio and DS5. Visual Studio debugger used to be very good when I was programming on Windows. I don't program on Windows anymore, but I kind of miss Visual Studio. So yeah. But these days I have to work with this piece of shit, so I don't know. Alright. So let's continue, I suppose. So I'm already streaming for an hour, and I think I want to make a small break, right? Because I need to refill my cup of tea. And after the break, I'm thinking we're gonna start integrating our renderer into the application, right? So we have this renderer, and we need to replace the static memory regions with that specific renderer. So we're gonna probably go and just remove these things, and we'll try to compile. We're going to follow the compilation errors, and where compilation errors occurs, we're going to be replacing them with the renderer that we initialized in here. So far so good, I suppose. So I use it sometimes and I don't want to miss it at all. Do you use GDB often? How often do you use GDB? Yes, so you prefer GDB over Visual Studio. To be fair, the Visual Studio debugger that I used is from 2008, when, you know, even maybe before, you know, when Visual Studio was good. So I have good memories about Visual Studio. I haven't used modern Visual Studios, but I heard that they're horrible. So yeah. It's kind of sad that in 2021 we don't have a good debuggers like at all for any platforms. It's just really, really weird. Like, how are we supposed to be doing software development? Does GDB have some wrappers with GUI? I'm kind of not sold on the idea of wrappers, because how do you integrate with GDB? How do the GUI wrappers integrate with GDB? Do they just parse the standard output of GDB? Is that the way to interact with it, or is there any other better way to do that? It's just like, this entire idea looks really strange to me. I think I know that you can script GDB with Python. Maybe on the Python side you can at least open like a socket and connect the GUI via the socket. So I don't know. And also the front ends for GDB, so they introduce like another moving part, and now you have to think, is your GDB compatible with that GUI thingy or not? It's just like, the debugger I think should be like one single uniform thing, so you don't have to think about like moving parts and stuff like that. You know what I'm talking about? So have you tried debugger in VS Code? I cannot use VS Code, I'm sorry, it's too slow for me. But I never tried debugger in VS Code. Alright, so I think we need to make a small break. Okay, so I was brewing tea and I realized that there is some sort of a vulnerability in here, I think. You see, the user is able to control these parameters, and these parameters actually define how much memory you can allocate, which is fine. So if the user want to allocate shit ton of memory, right, and they have a machine to do that, I think we should allow them to do that, maybe. I don't know. But here's the thing. What if this entire expression overflows? Right, none of them separately overflow, but the sum overflows. What that means that you're going to end up allocating less memory than these sizes, which then potentially down the line will result in the code trying to access memory that is not the program is not allowed to access, right? Because you allocated less memory than you wanted. All right, so how can we approach this kind of thing, right? So we can try to detect overflow somewhere here, right? But also you can overflow not only here, you can overflow in these individual things. So you have to check for overflow in a lot of arithmetic operations in here, which is kind of meh. I don't want to do that, so I don't really want to spend too much time on it. So maybe we could introduce a concept, right? So we have a concept of default tile width and tile height, and the default grid width and grid height. So what if we introduce the concept of the max tile width px or something, right? And max tile height px, right? And similarly, right, so we're gonna have max of these things as well. So this is going to be max, and we don't know what it's going to be yet. We don't really know what it is. So, and here's the idea. We are never going to allow the user to set the value more than this. And we're going to make sure that these max values are picked so that even if you set everything to maximum, the final memory size is not going to overflow on 60-bit architecture. You know what I'm talking about? So we need to pick the max sizes that are reasonable, right? They are reasonable, so this is roughly what the user may want to have. But if you just like multiply them and add them in a very naive way without checking, you know, overflow and stuff like that, it will just work, right? So without any overflows. So that's basically the idea I have, because I don't really want to spend too much time writing the like checking for overflow on each individual multiplication, on each individual sum, you know, right? Because it's fucking tedious. Like I don't want to do that. Come on. And then if you detected overflow, what do? How do you report that to the user? So you have to add so much like code just to check for this kind of stuff, and I don't want to do that, right? So I guess we're gonna have a concept of the maximum tile width and a maximum tile height, and also grid width and grid height, and we're gonna make sure that if you set the values to these values, it's gonna be big, it's gonna be huge, but it's not gonna overflow 64-bit number. Make sense? So, and maybe we will prevent some vulnerabilities, because basically this is vulnerability that allows the attacker to control where the program will touch the memory in the places that are unmapped, right? So it just allows the attacker to say, go touch that memory that you're not allowed to touch. And if something overflows, you may probably target the execution at memory that is mapped and start, you know, writing things in there. And that's no good. That's no good. I don't think we should allow that. We should rewrite our program in Rust as soon as possible. As soon as possible. Rewrite everything in Rust. Touching and not places to flash. Yes, exactly. So what we're gonna do, I think I want to just estimate this kind of shit, I guess. How can we even estimate that? Maybe we could port this chunk of code to Python, right? Python actually grows, like it has like long arithmetics, so you can do shit like this. Well, I mean, it's actually, yeah, so you can have very big numbers, so it never overflows, which is nice. So, and we can just port this chunk of code to Python and just play with these parameters and pick the ones that don't overflow, right? So let me just grab that and estimate.py, right, there we go. Estimate.py, there we go. So do you guys like Python? I love Python. Python is my favorite language of all time. Right, so user bin environment Python 3, I suppose, right? So we're gonna have Python 3. So we're gonna define the function render realloc. So estimate memory size. That's basically how we're gonna call this, and I'm gonna just do it like that. So then we are accepting parameters in here, and that's gonna be the thing. There we go. So we don't need to have that. We don't need to have that. We're gonna be only assigning atlas width in pixels. So we need to have this thing somewhere. Let me grab that stuff, atlas width. So both of them are 4. So I can just say that this one is gonna be just 4 by 4. Okay, good. Okay, good. So here we're estimating things in bytes. So I'm gonna just grab that, and I also need to have a size of RGB32. So I think I'm gonna just turn it into a variable, right? I'm turning it into a variable, and I'm gonna say that it's equal to 4. You have 4 bytes in here. So we don't need to initialize that. That is not important. We're gonna do that. Okay, so we have another one, size of BLTR. So it's going in similar fashion is going to be just 4. There we go. So then we have a grid width in pixels. So let's just remove that. Boom. Size. Okay, so and then we're gonna have memory size. We don't need to allocate any memory in here, and we don't need to subdivide anything. So the only thing we care about is the memory size, and essentially this is what we can return in here. And we can also query replace and get rid of all the semicolons. So there we go. We ported the memory size calculation to the to Python. So now we can call this function with like different parameters and just see that they're gonna overflow or not gonna overflow. And of course you don't have to have these things in here. I think that's fine. Looking good so far. Can I just run this script in here? So I have to first run Python. I don't know why I want to use Emacs for this thing. Okay, so do I have estimate? Okay, so maybe I don't. Let's not do that. Let's not run Python from Emacs. I don't think it's a very good idea. So I have this thing which is not needed, and maybe I can start IPython. So do I have IPython of the 3rd version? Man, it takes long to start up. So this is the 3rd one. Can I import everything from estimate, like from this? From estimate, oh my god, why is it so slow? It's blocking. Estimate, okay. Import everything. So can we estimate, oh my god, estimate memory size, all right. So the first 2 things in here is the tile width and tile height. So let's say that we want to have the tile 64 by 64 and the grid 10 by 10. So this is how many bytes we have, right? So this is the bytes. So maybe for the comparison, what we want to have is 2 to the power of 64. So our value should not exceed. That's a huge value, actually. So to exceed 64 bits, you actually have to do a lot of work to be fair, I think, right? So, okay. So can we now say that, how huge do you want a tile? I think tile like 1024 by 1024 is reasonable, and we still don't overflow, actually. Okay, that's cool. That's pretty cool. Do you want a bigger tiles? Keep in mind that a tile, right? Tile, where is the atlas? Is a single square. So we are controlling the size of this single square. And I just set the size of that square to 1024. 8K textures. Okay, we can try to make it 8K. Why not? 8. Oh my god. Still doesn't really overflow 64 bits. So we can have 8K textures. You're using 32-bit integers, not 64, I think. Let's take a look. We can actually double check that. So render realloc. Where is the realloc? So the integers that I'm using size t, right? So now I can try to do the following thing. I can do main and just take a look at the size of the size t. Size of size t. There we go. So this is going to be that or something like that. And can I just run the entire thing? I'll probably have to go here. Hopefully. So the size of size t is 8 bytes, right? It is 8 bytes. 8 multiplied by 8, 8 bits, 64. The size of size t is 64. So, and if you Google up what is a size t, right? What is a size t? It's an unsigned integer type of the result of size t. So, size t can store the maximum size of a theoretically possible object of any type, including array. So, because of that, on 64-bit architectures, it is usually equal to 64 bits because it's supposed to store like the biggest size of an object. So, on 64-bit architecture, it's going to be, you know, that. Okay. So, we can have 8K textures, right? But how big can we make our grid? Can I make it 100 by 100? Okay. 1000 by 1000. It still does not overflow, right? 10,000 by 10,000. At which point is it going to start overflowing? So we could probably, you know, grab this thing and maybe create some sort of function that will help us to do this kind of stuff. So estimate memory size. Maybe the thing I want to actually return, in fact, is that. Yeah, so we can do print. So memory. Okay, size. So this is that. Max is that how is this how we use f strings in Python? Do we have any professional Python developers in the chat? And maybe I also want to print something like overflow, which is going to be okay. So memory size is going to be like this. Memory size. No need for semicolon. Oh, you don't like me putting semicolons? Okay, sure. Just a second. Can we replace? So can we replace this thing with that? Boom. Okay. Okay, and then this thing. Okay, there we go. So looks good to me. So yeah, I want to actually save these things. Max size. All right. So max size. And how we're going to check for the overflow? We're going to say that memory size is greater than the max size, right? So that should be roughly it, right? If I understand everything correctly. And I wonder if I can just overflow the entire thing. Overload, I mean. Reload. Oh, almost forgot. There we go. So let's quit the entire thing and let's reload. From estimate, do that, and yep. There we go. So it still does not overflow. I wonder if I can do something like 24, also 24, and just, you know, 8K by 8K as well. And it still does not overflow. So I can actually, yeah, the values can be quite huge and they're still not going to overflow. which is rather cool, I suppose. All right. So I'm thinking, can I just have this thing where I just do something like this? I might as well, yeah, I might as well use a single value for all of them. So this is going to be a single big value, right? So it's going to be a single big value. There we go. So there's still no overflow. What about 16? Still doesn't overflow. 32 still doesn't overflow. And I think it starts overflowing at 60. Yeah, it starts to. Okay, so this is how big I can make this kind of shit. So, and the size, the maximum size is 32,000. Right, 32K. Right, and it's not gonna overflow. So this is the value that we can use for both tiles and grids, if I understand correctly. So, and yeah, if the user wants to, if the user have this amount of memory and they want to do this kind of stuff, well, sure, all power to them. Like, I don't mind. It's just like I don't want my program to overflow, so potentially you can make it touch the memory that it's not supposed to touch, right? If you have a huge, thick, juicy memory and you want the program to touch it in the right places, I'm all for it, right? I'm not gonna judge you for that. So it's just like the most important thing for my program is not to touch the places it's not supposed to touch. Right. What if I want a bigger texture? Well, here's gonna be the idea. We're gonna set the parameter, right? So the maximum is gonna be this, right? And I think the maximum is rather reasonable, right? So this max is rather reasonable. If you want something bigger, you can go into the source code of the program, change the maximum yourself, but if you change it, you are going to be the you're going to be the one who's responsible for all of the buffer overflows. So that's going to be the thing. So basically, I disavow any buffer overflows from this specific piece of code, by introducing the maximum. But if it's not enough for you, and maybe you have 128, bits architecture, and you know what you're doing, go ahead, modify the code, recompile it. But now you're responsible for this thing. So basically, you break the warranty by modifying these defaults. Does it make sense? So if you want a bigger texture, you can do that. Sure, go ahead. But you take all of the responsibility on you. So sounds like a pretty good approach, right? So so this is the script that estimates this entire thing. And do we want to like attach that script to anything? That is very, very interesting. I hope I didn't make any mistakes in here. So, okay. So, 32. Relook. So we're gonna do a couple of assertions in here. We're going to do a couple of assertions. We're going to assert, first of all. Oh, here's another interesting thing. Do we want to allow the user to set 0 to these things? I don't think it makes sense, right? So I think the 0 should be incorrect value. So we're going to assert that tile width px is greater than 0, but also it is less or equal to the max tile width px. There we go. Maybe I'm gonna actually do it like that. There we go. So we're checking that. We're checking that at runtime. You're supposed to basically tell the user that they're wrong if yeah. So essentially you will get those parameters from the user. You'll have to check if they are in correct range before calling these functions. But just in case, within these functions we're gonna add asserts, right? So it makes sense to me. So I'm going to replace width with height. Right, so there we go. So here's the width and height. And the same is going to go for the grid. So I'm going to assert that grid width TL is greater than 0, and I'm also going to assert the grid width TL is less or equal to the maximum grid width TL, right? So it's allowed to be equal to that, but you cannot be greater than that. So I'm gonna also query replace width to height, and there we go. So we range checked everything. And here comes the fun part, right? So we're gonna be statically asserting max tile width to be equal to this thing, right? So and we're gonna do that for all of them, right? So basically it is needed when you who wants to have a bigger texture modify these values within the source code, you would get a warning, and you will have to basically confirm that you know what you're doing by removing these static asserts. You see what I'm doing here? So I made sure that with these maximums, this is not going to overflow, right? Then I put an assert in here, and if you change something, we're going to warn you, okay, buddy, this is on you. So we don't take any responsibility for any buffer overflows because of you changing the parameters that were double checked that they're not going to overflow. Make sense? So that's going to be the idea. So grid width TL, right? So and grid height TL. Alrighty. So what we're gonna put in the messages in here? That's a very good question. Do we have anything to do? So the max. How to say that? We need to word that. The maximum values are carefully picked, so the final memory size does not overflow. Does not overflow 64-bit unsigned integer, right? Does not overflow 64-bit unsigned integer. By changing these values, you confirm that you know. Okay. Remove the static asserts below. Is that how I spell below? I just realized that I have a huge brain fart right now. Yeah, okay, so I think I'm already tired. Remove static asserts below to confirm that you know what you are doing. Okay. The maximum values are carefully picked so the final memory size does not overflow 64-bit unsigned integer. Remove the static asserts below to confirm that you know what you're doing. So make sense? Okay. Have has changed. Please. Okay. So maybe I'm gonna just say that this thing has changed. Has changed. Unexpected. Unexpected. Expect the unexpectable. Okay. Am I being too overcautious? Cautious. Is that like? Is this important to really care about? Right. I don't know. Because is this too much? Because I think it does make sense, right? So we're dealing with the user input, right? And the user input actually controls how much memory allocate and how we basically redistribute that memory. And we don't really want the user to have too much control over that, right? So we just want to be able to, you know, to let the user tell us what kind of sizes of the textures they want, but we don't want to give the user full control of what's going on, right? And if the user manages to overflow 64 bits, well, that's kind of no good. Nobody has space for it anyway. But that's not the point. Like, ideally, I think ideally, we should allow the user to allocate as much memory as they want. You want to allocate like terabytes, like petabytes of memory. Sure, if you have this memory, go ahead and do that. The only thing I care about is the 64-bit overflow, which actually makes our program behave incorrectly. That's what I care about. I don't care what the user has or doesn't have a memory. I don't give a shit. Right, so it's your computer, your memory, do whatever you want with it. What I do care is my program working correctly, right? And if the user manages to overflow 64-bit integer, well, my program stops working correctly, and it has nothing to do with the amount of memory. So, you see what I'm talking about? So that's the only thing I care about. I wish I could just allow the user to set any values in here, but it's just like too much work for me to check if nothing overflows and everything works correctly. So I rather just check it once beforehand and never think about it. That would be actually perfect in my opinion. Alrighty. Okay, so what do we have in here? Okay, so we probably need to set these things to 32, 24, 32, 24, right? 32, 24, 32, 24. There we go. Do we have anything else? Okay, that's cool. Mine gut. All right, so let's remove that and let's go over. I wonder, let's actually try to hook up the user input into these values, if you know what I'm talking about. So yeah, so we already can set the path to the PNG files and whatnot. So I think it makes sense to now allow something like strcmp param, so the tile width. Yeah, let's have a tile width. You know what, I think it makes sense to first modify the help function, right? So in the help function, here are all of the parameters we have. Right, so the next parameter, so the idea of printing things like that is actually kind of cool. It looks cool, but it makes the lines, you know, too long. Live parameter changes, yeah. So if you run it with live, this is how it looks like. So if you run it without live, it's just gonna render things in offline, right? You see, it just spits out PNG. But if you want to see the live parameter, so this is how it works. So it will start the window and everything. So that's basically what we have in here. So I think I want to actually slightly change the approach we print the messages, right? So I think the description should be printed on the next line, right? So so this is fprintf stream 1 2 3 4 and maybe 1 2 3 4 to indicate that this is the description, and there we go. So yeah, I guess it will make a little bit more sense. And if you have like too long of a descriptions, it will make it easier to split them and stuff like that, like in case of live. Right, so let's actually go ahead and do that. I think it's a generally pretty good idea. So fprintf, we need to change the style of this thing. 1 2 3 4, 1 2 3 4, boom. Boom, there we go. New line. Cool. So, and in here, so here's the line that is related to the same flag, so we can just keep it like that. Okay, that's perfect. Perfect. So let's remove this entire thing and okay, so fprintf string 1 2 3 4, boom. So this is going to be the new line, and fprintf stream 1 2 3 4, 1 2 3 4, boom. There we go. So is that a better approach? Is this a better approach? Is this a divine intellect? I wonder. It kind of is. It actually looks good. I can't complain with that. So, and we can even put more information for each individual flag in here now, so which is super convenient in my opinion. So yeah, it's a good way to print all of that. All right, so maybe the time has come to do a committee and maybe even pushy. So let me see. So we're gonna, yeah, so this is the dynamic. I'm gonna have a separate commit for the help, right? Where is the help? There's no help, nobody's gonna help me. All right, so change the help output format. There we go. I'm gonna push that right into the repo. Right into the repo. Yes. And let's also commit the renderer thingy. Right, let's also commit the renderer thingy. Introduce the renderer structure. And we're gonna push that as well. What do I want to do this with this Python code? Do I want to include it? I feel like if I'm going to include it, it's not going to be particularly useful. So it's like a one-off code that I'm going to just basically throw away. So, oh, an entire thing and another thing. Well, it should be fine, I suppose. All right. So let's remove all of that. So we don't need this shit anymore. Cool. Now let's go ahead and add more flags in here. Specifically, I want to add now the tile width flag. So this is going to be width, and then go the width of the tile in pixels. The width of the tile in pixels. So we can actually set the default, maybe even. I don't even know if we want to set the default, because I think that's kind of a useful information. And we can say default is going to be equal to that, right? And this is going to be default tile width in pixels. There we go. And the maximum, right, is going to be the max tile width. So now let's see if it's going to work. If I do help, there we go. So the width of the tile in pixels default 64, maximum is this. Perfect. So we're even using the same constants to actually print the help, right? So they become part of the help. So, but the problem here is that you can't use that, right? So you cannot set anything in here because we don't handle that parameter yet. So let's go back in here and so if you encounter TW, right? If you encounter TW, and we don't have any parameters in here, we're gonna say, well, no parameter was provided. User, you did a fucky wacky. Oopsie doopsie. Argument is provided. Provided. Thank you so much. Okay, so and now the argument is essentially shift args argc argv. Cool. So that's the interesting part. We need to parse this argument. We need to parse it very carefully, right? So because we don't want to fuck up the size that is used in calculating the memory and in calculating the buffers, right? We don't want to fuck up this kind of stuff. So we're gonna probably use the standard C function for that. So it's called str2ul. I think that one does make sense and it's part of the standard, right? So this one is rather convenient. So we also want to make sure that, well, I guess that's fine, right? I guess it's fine. So we have to provide the argument. So here's the argument. And we also have to provide the end pointer. And end pointer is actually rather interesting, right? So basically, how does str2l parses your number? So we have a string, right, that points to this sequence of characters, right? So, and how does it parse it, right? It starts iterating until it sees a known character or null. So at the end, you have a null in here, right? And as it iterates, it basically adds the characters it sees to the final result, right? So it just adds them like this. And it does that until it encounters something that is not a digit, and basically returns you this value and a pointer where it stopped, where it first encountered an unknown character. That's basically what it does. It's actually very, very simple, right? So, and you can use this thing to do some sort of checks, right? For instance, when the user provides a string, I expect the entire string to be a sequence of digits and nothing else. So if after I parse the number, I see something that is not a null terminator at the end pointer, that means that the string is not the correct number. So I can then tell the user, bruh, you did not provide the correct number. So does it make sense? Does it make sense? I hope it makes sense, because if it consists only of digits, the end will point at 0, and that's exactly what this end pointer is. So it's basically a variable through which this function returns you where it stopped parsing. Right, so that's how it works. So, and we're going to provide a pointer to that, and the base, we do everything in the base 10, and there we go. So this is the argument as the string, and this is going to be the argument as the UL, right? So that's what we have in here. Cool. So, and for instance, if end pointer so I think yeah, there is also an interesting situation. You can check that you parsed everything correctly if end pointer points at null. If it doesn't point at null, you can say that this thing is not the correct number, right? So you can do param fail, fail program param, and you can say this is not a correct number, right? And we can provide arg as a sister. There we go. So this is a function that will basically automatically fail with this error message. Okay, but here's an interesting thing. What if you have an empty string? The function won't parse anything. It won't parse anything at all, but it will still point at null. So we need to have another check, right? So if the string is empty, end pointer is going to be equal to the beginning. So if arg sister not equal to end pointer, or end pointer not equal to 0, only then we're going to say it's not the correct number. If the number is parsed as bigger than inmax, does the pointer also stops moving? Maybe check error no for extra safety. So here's how it works, right? So we need to refer to the documentation to know about overflows. So overflow, right. So function returns either result of the conversion, or there is a leading minus sign, the negation, the result of the conversion value would overflow. In a later case, in a case of overflow, strul returns ulong max and sets error node to e range. Precisely the same holds for strul. Okay, so basically if the number is too big, it's never gonna be bigger than ulong max. It's never gonna be bigger than ulong max. And ulong max is probably bigger than max of this thing. Do we really need to check anything? So basically the user basically spammed with digits. And if the user spams with digits, we're gonna go into the path of saying, oh, you provided a value bigger than max style width. And that's precisely true. So I don't think we need to check anything per se, right? But one of the things we may want to have is maybe set error no to 0. I don't know. Maybe another thing we can check. Let me see. So Right. We're gonna statically assert. That ulong max. Right, and max tile width is less than this, right? And then just ignore it basically, because then if arg ul I'm falling asleep. I need more tea. So what do we need to do next? I think the next thing we need to do, we need to assign arg-ul to the tile width. Right, that's basically what we need to do. We need to assign it to the tile width. So let's quickly do that. Tile width pixels, arg-ul, then here, if tile width pixels is greater than max tile width pixels, we need to throw an error, right? So param fail, program the parameter, the provided tile width exceeds the maximum allowed value, and we can even say that value. I think you can have to do it like this. So max tile width pixel. So this is the first thing, and another thing we probably need to check if it's equal to 0. Tile width pixel equal to 0. Param fail program param the provided tile width. Okay. Tile width cannot be 0. There we go. Because if it's 0, that means the final memory calculation is not going to be correct. So that's basically the steps we need to take to parse everything, right? So we extract the argument, then we use str to ul. We check that we parsed a number at all, right? We check that we parse the number at all. Then we're assigning it to this thing, and then we check that it does not exceed the maximum available size. If something overflows, that means it's going to be bigger than this thing, and we're going to fail anyway. If it's equal to 0, it's also not allowed, because yeah, memory size calculation is not going to be correct. So we probably have to repeat it 3 more times, right? For height, for tile height, and also for grid width and grid height. So it would make sense to extract the parsing and check into some sort of like a separate function at some point, right? Because we don't really want to repeat this kind of shit too often. So yes, so let me see if this entire stuff compiles. Okay, so what do we have? Arg sister. So what else do we have here? Ulong max. So this requires limits. Let's include the limits. So limits.h. What else do we have in here? Okay. So we probably need to say something in here. If str to ul overflows, it will return ulong max and set error no to eRange. Right. So but if max tile with max is always less than ulong max, we always fail with the max exceed error, so there is no need to check for that. Toggle truncate lines. There we go. Overflows, it will return ulogmax and set error node to e-range. But if max is always less than ulogmax, we always fail with the max exceeded rate, with the exceeded maximum allowed. With the exceeded maximum error, so there's no need to check for that. So that's basically the reasoning behind that, right? And that's why I statically assert specifically for this situation. Static assert are really, really useful for documenting these kind of things. You know what I'm talking about? So you're not just leaving a comment, but you also check for the invariant at compile time. So if the invariant changes, the programmer can go back here and like verify that, oh, okay, in fact that changed at some point, so maybe we should do something else. So I really, really value static asserts. I think they're very valuable mechanism, especially for such unsafe languages as C, right, where it is super easy to make this kind of mistakes, and yeah, it is very valuable in my opinion. So yeah, what do you guys think? Do you use static asserts at your work to check for this kind of stuff? I personally find them very, very valuable. I don't know, maybe I just I don't know. Okay, so let's try to compile the entire thing, and everything seems to be working. Okay, so can I now test this kind of stuff? So if I do help, and then I'm gonna say TW 128. So oh, okay, 128 is not the correct number. Cool. So if it's equal or otherwise not. All right. So if I try to do that, and yep, it kind of worked. It did the trick. So can I set it to 0? Tile width cannot be 0. Okay, so if I set it to a very big number, tile width exceeded the maximum allowed value, this thing. And obviously I can put it like that, right? So it's 100% gonna overflow, and it still says that, yeah. So you see, in case of overflow, it always tells that you exceed the maximum allowed number because the invariant, this specific invariant, is true. Right, if it was false, maybe then we'll have to check for that. But since this value is way less than maximum thing, we never have to check for that, so whatever. Makes sense? I think it makes sense. So... It's pretty powerful, isn't it? Thinking this. Okay, so we can probably maybe check for some things in there, I don't know. Okay, go. So we need to do that for the rest of the things, right? We need to do that for the rest of the things. And the question is, how are we going to be extracting? Where exactly we're going to be extracting all of that, right? So I think maybe the part that is performing the actual conversion should be here. So this should be extracted to a separate function, but maybe the ranges have to be checked outside, right? Maybe they have to be checked outside. Yeah, I'm a little bit tired, chat, so I think I'm gonna go and make a small break and maybe refill my cup of tea. Think about the whole situation a little bit more. Maybe we're gonna still get rid of this condition because it doesn't really make it super easy to factor this entire process out, but we want to really factor it out because we'll have to repeat it like 4 times, and this is not particularly convenient, right? Because we have 4 parameters for which we have to check all of that stuff. Right, so yeah, let's make a small break, and all right. Let's factor this thing out. So what I'm gonna do in here is probably create a function that parses size for m. So let's actually call it something like size for m, maybe for m size, whatever. So, and I'm gonna straight up take the entire thing in here, right? and copy paste it inside of that function, right? So it accepts a bunch of parameters and it will fail the compilation, and that's precisely what I want. I want it to fail the compilation so it will tell me what I need to pass in here. Make sense? So let's go. Okay, so this is the first thing. We need to pass arg sister. Const char arg sister. There we go. Anything else? Program and parameter. Okay, program is the name of the executable because we use it in error reporting, so it's quite important. So this is the program, and then we have the parameter. Parameter is the flag that we're currently handling, right? So, and in here we're really setting this entire thing, but I think in our case we should not set it, we should just return it. So this is going to be size t. So, and what I'm trying to return in here is just that, right? So this is what I'm returning. And I don't need to set that. I need to set that. And okay, so here is the thing. Maybe I need to actually assign it to some sort of a result. Arg ul, right? And in fact, we are checking the result. So there's no need to say that it's a tile width because we know the parameter, and parameter is like the flag. So yeah. So we have to do something like this, and then we just return the result. So is it gonna work now? It kind of does, but not precisely as I want it to work, actually. So here we do the range check, right? We perform the range check. And I think for the param size, we're gonna provide the minimum and maximum like this. So this is gonna be min value, right? So min value and also max value. And quite important, we're gonna assert that min value is less or equal max value. So you don't provide any stupid shit in here. Okay. So we also may try to assert that the max value is not bigger than u long max. You know what? I think we need to check for the e range, right? So it will make it kind of easier to check for e range. So right. So if this thing is that, if this thing is that, so how are we gonna approach all of that? What I'm thinking is if arg ul is equal to u long max and error no is equal to e range, right? We're gonna say that you know, parameter overflow. So integer overflow, I suppose we can say that integer overflow. So maybe we can also say not a correct number, integer overflow. Here we know for a fact that there's no overflow, so because of that we don't need that shit anymore. And here we're gonna do the following thing. So min value less or equal than result, and result is this thing. And if it's not, right, if it's not outside of the allowed range. So outside of the allowed range, and we can say something like this, I suppose, and we're gonna have a min value and a max value. There we go. Okay, so this code is also very simple. I really like that it's also very simple. Right, so we try to parse this entire thing, not the correct number, integer overflow, then if it's outside of the range, we say outside of the range, and we know exactly what parameter we're talking about because we're passing the name of that parameter for that function. So everything looks tight, and I really like it that way. Okay, so let me grab the param size thingy, right? The param size, and what we're gonna do in here is just provide the program. Here's the program, here's the parameter. The arg size is gonna be this thing, right? So this is that thing. So the minimum value is going to be 1, right? It's going to be 1, and the maximum is going to be max, what is it called, tile width in pixel, right? And what we're assigning here is the tile width in pixels. What ZU used for? It's used for values of the type of size t. Here's the thing, size t on different platforms is a different alias. So if you just use d, which is for integers, on some platform, or maybe u in this case, so we know that it's unsigned integer. So if you just use u, on some platforms it may not work because on some platforms size t is bigger than unsigned integer. It may be unsigned long integer or something like that, you know, things like this. So because it's not like a very stable type. So specifically for this kind of situations, the C standard introduced a special format argument called ZU, which is for sizes. So on different platforms, it's going to be expecting the correct type. Does that make sense? Right. So that's basically what it is. And size t is the type of the size of operation, right? And usually size t is used for the sizes of arrays, of sizes of the buffers and stuff like that. So it's a special type for the sizes, right? And ZU is for printing the size type. Hopefully that makes sense. Yeah, you're welcome. Okay. So, okay, so we're assigning this thing in here. We're also providing the maximum and minimum parameter. And I think I can just, yeah, I can just like remove this entire thing. And we're good to go. All right, so we have param size, and this thing is reusable across several arguments in here, and it's pretty simple. I really like it. Okay, so let's go ahead and just recompile the entire thing. So it complains about some things. So not the correct number. Oh, this is because we don't have to provide anything in here. All right, so what do we have in here? I want to check a bunch of things. So TW, no argument is provided. 0, outside of the allowed range from 1 to 38. Okay, so if I put 1, it is fine. If I provide 32, 7, 68, okay, it was fine. What if I provide a bigger one? Okay, so it's outside of the allowed range. What about overflow? Integer overflow. Okay, that's cool. And what about incorrect now? It is incorrect number. So everything is pretty tight, I would say. So we checked for all of the possible situations. Pretty cool. So, and now we can do that for the rest of the parameters, right? So we have width, and I want to have the parameter for the height. So it's going to be h, height. So the height of the tile in pixels. So the default one is a height, and this one is a height as well. So there we go. We have that. And the way we're going to handle that is we're basically going to copy paste the entire thing. Right, so now it is height. So, and then we're assigning to the height, and the maximum one is the height. There we go. So now we hand in height. Nothing special. You happen to know what the problem was? I think the problem happened because I was using a huge array as the result value. I think that was the problem, and I think it kind of blew up the stack in some sense, or maybe actually forced the program to touch the stack in places where it's not supposed to touch. I didn't really look into the situation too much, I'm sorry. But that's like the working hypothesis of mine. So, all right. So this is going to be the height, and we're ready to go. All right. So let me see. So it's going to be rank help. To be fair, maybe we should put this on. Yeah, it would make sense to put it on the same line. To be fair, I think having too many lines in here is not a particularly great thing. So I want to just put it like that. So this is going to be default. And the maximum, right, so it's default and maximum. Okay, so we're gonna remove that, and maybe here's the idea. I'm gonna do query replace width with height. Boom. This one is going to be H. I'm curious to satisfy it. Yeah, it's kind of strange that the compiler didn't help me in that specific situation, like, at all. So, because, yeah, they could have at least tell me that I'm doing something wrong, because it's supposed to be like a safe language and whatnot, but it's just like straight up seg faulting is no bueno in my opinion. Alright. So I have enough of this kind of bullshit in C already, so... Can I have once in a while like a language that actually help me? I don't know. So, that looks a little bit better, right? So we have width of the tile in pixels, default 64, maximum, blah, blah, blah. Okay, cool. So, and I want to have a similar thing for the grid, right? So here I'm gonna create a thing. So this is gonna be called grid width, the width of the grid in tiles. That's very important. So maybe I'm gonna even capitalize this thing to actually, you know, make sure that the user understand what the fuck is going on. So this one is a grid in tiles, maximum grid in tiles. All right, and similarly, we're gonna have this thing like that, and this one is gonna be H. There we go. So let's rerun this entire thing. So default grid width and tile undeclared. Oh wait. Oh, okay. So that makes sense. All right. So if I do wang help. Okay, so we have all of the necessary parameters in here. So it's really useful that it tells you the default value and the maximum. So there is a discrepancy here between this style, right? We use this kind of default, and here we use different kind of default. So I would like to go back in here and just change the style a little bit, right? So this is going to be something like that, right? So the style is sort of like universal across the whole thing. So I'm not sure if I want to put this stuff on a single line. So this is a creative process. I'm like an artist. Right, there we go. So that's a good looking help page, isn't it? I think it's pretty good. Bring this help message to the std, thanks video code, live animated and live. Here's that stuff, and here's the parameters and stuff like that. That's pretty cool. It tells you like what expected, maximum, minimum, and some other shit. So, and the maximum was picked, so if you set this maximum, it's not gonna overflow the buffers or anything like that. So everything is very, very carefully picked. Okay, so let's do the following thing. We have that stuff. It's gonna be G, and I'm gonna query replace tile with grid. And here's the interesting thing. This is tile in pixels, so I need to replace pixels with TL. And there we go. So we have that now. So in here, I'm gonna be taking the height and it's gonna be just so, and I'm gonna replace width with height. There we go. And if I recompile the entire stuff, let's see if it's gonna work. So can I do G 1000 by H GH 1000, and everything seems to be okay. But if I put like this thing, GH integer flow, I really like that it also tells you the flag and it also prints the help. That's a good looking help. Yes, user experience is over the roof. User experience is pretty tight. So now I'm going to simply commit that, right? There's nothing much to do in here, I suppose. So introduce the flags for tile and grid size customization, right? So grid size customization, I'm going to push that right into the repo. So once we've got these kind of things, oh, by the way, I just realized that we never actually use the parameters we provided. We never actually use them. So what I'm thinking is that maybe we have to put it in here. But also I have to be super careful, by the way, because if I allocate too much memory, that might kill my entire system, right? So I'm not even sure what I'm gonna do in here. Right. So here is the renderer. So I set the parameters to the renderer. I allocate all of the necessary memory. And maybe the things I'm going to print in here are going to come from the renderer itself, you know? Something like this. So let me just quickly, boom. So now we are printing stuff from the renderer itself. And then we free in the renderer. We still don't use the renderer, right? Both of the processes here, they only use the global one, but we're about to change that soon. We are about to change that. So let me try to recompile. On this thing now is ZU. There we go. So this is ZU. Cool. So now if I try to run the wank thingy, so it is using the default parameters, and then if I try to say tile width is going to be 128 and tile height is going to be 128, so tile, it actually used 128 and it allocated like a different thing in here. You know, now we know the size of the memory in bytes. Right, so we can actually print that. So we can say something like memory size in bytes, ZU, and it's going to be memory size. So we can even print how much memory the renderer is going to use. I think it's kind of useful. Right, so let's quickly do that. Yeah, so this is how much memory we're using. And if we you know, allocate more memory, so this is the thing. So this is kilobytes, 9 megabytes. Okay, that's pretty cool. 256, and yeah, the more we use the bigger the tile, the more memory we actually use. Everything works relatively well. The only problem is that the actual applications don't use the new renderer, right? So we need to go through the entire code base and replace the current renderer with the new renderer, right? And it's pretty like a routine process, I would say. It's just like, yeah, replace call to that thing, from that thing to that thing. Which plugins do you use to display relative numbers? None. It's the thing that comes with Emacs. You can Google up Emacs relative numbers and the result will tell you what you have to do. Yeah, I'm using them to actually jump along. Well, we have this question answered in FAQ. Check out FAQ. Check out FAQ. So essentially, in Emacs, you can repeat commands. So command up and down, you can repeat them several times. And for example, 13 in here indicates that I have to repeat up 13 times to actually jump to this line. There we go. And I did. So that's basically what I use it for. It's the same thing as in Vim. In Vim it's the same thing. And it's a built-in feature of Emacs. You don't really have to install anything. It comes out of the box, at least in the version of 27.1. It's probably old version. I haven't checked the latest Emacs. I don't know. I kind of hesitant on updating my Emacs because with each release, Emacs becomes slower and slower and more broken, which is actually really worrying. So I don't know, maybe at some point we're gonna switch to something else. If I ever gonna switch from Emacs, I'm gonna switch to Vim, I suppose. Right, because this is the second editor that I know. And to be fair, Vim doesn't really become worse over time, at least not as fast as Emacs. So Vim degrades slower than Emacs. So what we need? We need to do the compiler assisted refactoring, and I wonder how much time it will take, and do we even have time for that today? Probably not. All right. So wire up the user provided parameters to the renderer realloc. Right, so that's basically. Do you have any specific advice for someone who's interested in programming and would like to start with C? Just go ahead and do that. That's a very good and specific advice that I can give you. Just do that. All right, so I'm just wondering how much time it will take to replace everything. I'm just a little bit worried that it's gonna take too much time. You know what, I think, yeah, I think we did the most interesting part of this entire stuff, of the memory allocation, like actually created a structure. So the rest of the things we need to do is basically remove these arrays, right, which is going to remove these arrays, and that will cause the compilation error in all of the places where we use these arrays. And then we'll have to go and pass that renderer everywhere. To be fair, I have an interesting idea. What if we make the renderer a global variable? So refactoring all of that is going to make it a little bit easier for now. Okay, so I'm going to do the following thing. I'm going to literally do it like that. So renderer R, right, and it's going to be in static memory. There we go. And I'm going to put it to do pull the renderer out of the global scope, right? But for now, since all of the functions, they're sort of like designed to work with the global variable, it's going to be easier to refactor it like that. So, and then maybe off screen, I'm going to just go ahead and clean everything up and pull it out of the global scope. So for now, yeah, for now I'm just gonna keep it global. So because of that, I'm going to simply remove this thing, and there we go. All right. So yeah, so we have a global variable called R. Maybe I should call it renderer. Okay, so let's just call it renderer because it's a little bit better. Let's not call it R. Okay, so this one is the renderer. And the other one is going to be a renderer as well. So, okay, let's try to go through the compilation errors in here. And here is the thing, right? So here is the thing. I'm going to do the following thing. I'm going to have a renderer, which is going to be the pointer to the global renderer in here. And now I'm going to take the pointer to the atlas and then the size of the atlas in pixels. So these became the runtime parameters. Before, all of these things were compile time parameters, but now they are runtime parameters, right? So, and yeah, because of that, we have to do this kind of thing. We don't have to actually make it like this, right? So it's going to be like this. Right. So the reason why I assign it like that is because to make it shorter, right? So R is a little bit easier to type than renderer. All right, so do we have anything else in here? So this one is another situation. So I'm going to do renderer R, renderer, right? So, and this one is going to be just R. Do we have anything else? This is going to be R, R. So let's actually let the compiler tell me all of the places where I have to do that. It was actually rather surprising that it didn't tell me everything. Okay. Oh, and by the way, I probably need to remove all of these things, right? Because they became irrelevant. They are now provided by the user. So we don't need all of that. So we have max tile width, a default tile width. And none of that. The only thing that is going to be left here is probably atlas width and atlas height, and there's no reason for the user to even customize that. So yeah, so it's totally fine. All right, so let's go through all of this stuff. Yeah, that's precisely what I was talking about. Yes, sir, yes, yes, sir. So, and yep. So this one is, well, yeah. Boom, boom, boom. Boom, boom, boom. You know what? I think I can actually query replace this entire thing with this entire thing, like literally everywhere, almost, except when the max is needed. So, yep. Wait a second. Where was that? Yeah, I think it's fine. So, because it's a width. Let's not jump ahead of ourselves. I think it's kind of dangerous to do that. So, yep. So, and that's basically what we need to do in here. So this is basically a tedious work of going through the entire code base and fixing the compilation errors, right? I don't even have to think about that, so it's like I can zone out and just think about something. I can even listen to the music, I suppose, right? So love this kind of work, right? You can zone out and just replace things. Easy. Very good. Very good. So renderer, R, renderer, there we go. Because some of the things were before compile time parameters or global parameters, now they're not. At least not anymore. And they can be replaced at any time. That's the point of runtime parameters. So yes. So this is the renderer, there we go. So this is now that. Anything else? Oh shit. Oh yeah. So we also have to do this thing here. Renderer. To be fair, renderer is actually quite convenient being global, which makes me think, do I really want to make it non-global? Right? Because, okay, I made it global, but it's pretty convenient. So there's like a few changes I have to make. Maybe I'm gonna keep it global because it's super convenient actually. Yes. Kawai desu. So it's gonna do that. No, global variables are very convenient, not gonna lie. So this is gonna be something like that. Yep. Okay, so what I'm thinking is that I can actually do it like that, right? So renderer, R pointed to the renderer, and where do I use the renderer now? So I can just directly do that, and directly do that. And that's it. So, and here we have a memory size. And I guess that's it. So I refactored it. Now we're using the new renderer, apparently. I think that was actually super easy. I didn't expect it to be that easy. Okay, so I'm gonna remove the atlas and grid, right? So, and I'm gonna say, okay, regenerate them one more time. So here's the grid, looks good to me. Here's the atlas, looks good to me. So, and if I modify tile width to 128 and tile height to 128, it should be bigger now. Well, I mean, yeah, it's TH. So as you can see, it set tile width and tile height, so it actually allocated more memory and stuff like that. Let's take a look at the atlas. Atlas became bigger, and the grid became bigger. So we actually can customize these parameters at runtime without recompiling the program. This is actually very cool. And the live version, by the way, the live version uses the same renderer So that means if I put life in here, there we go. So now we made it bigger. And if you want to make it smaller, I'm not recompiling any program, so now you can make it smaller if you want to. Right, so that's actually pretty cool. That's exactly what was the goal of today's stream, and I think we achieved it. Right, so I think we straight up achieved it. I can actually make it like pretty big. And furthermore, I can do a pretty cool thing. So I can set the size of the tile 512 by 512, but the size of the grid is going to be 1 by 1. So it means we're going to have only one single tile. Let's actually test that without the live rendering, just to see if it's going to be fine. And so the whole rendering took, yeah. So the slowest part was actually generating the atlas. Oh yeah, atlas must be ginormous, holy shit. So atlas, yeah, that's the whole atlas, because each tile in this atlas is 512. But the final grid is just 1. So we have a situation when the grid is smaller than the atlas. Yeah, that makes sense. Right, so if I use the same parameters for the live version, oh my god, it's so slow. Look at that. Yeah, that's how slow it is. Holy shit, that is very slow. Why is it actually rendering it in such a... Well, I mean, that makes sense, yeah. Yeah, because the reason why it's slow is because we're parallelizing on the level of several tiles. We do not parallelize a rendering of a single tile. That's why it's slow. Right, so we can set like very small tiles in here. Right, so this is going to be super fast. But the amount of tiles, we can say like 100 of them. And this is going to be this size. Okay, so if I take a look live, so the encoding is probably shit, but that's actually pretty cool. Yeah, if you can see that without the encoding artifacts, it's actually super cool. I really like that, but yeah. So bitrate, yeah. Bitrate is kind of sus, not gonna lie. But I think we did it, boys and girls. We actually did it. I didn't expect it to finish within like 3 hours. I thought it's gonna take too much time, and it was already prepared to put some work off screen. But I think we did almost everything that I wanted to do on the screen. So we pulled the static memory out and replaced it with dynamic memory, right? So now renderer uses dynamic memory, and yeah, I didn't really have to think about it. And we also made it so more or less future-proof, right, from buffer overflow bugs, right? So because we crafted a specific maximum width and height values that will never overflow 64-bit integers. So that was kind of cool, not gonna lie. All right, so let's actually do a committee. Replace old renderer with the new one. There we go. And let's push that right to the repo. All right, so let's make a pull request for this thing. I'm actually super happy with the result. Oh, and by the way, I think in terms of to-do, I actually also finished another to-do that I wanted to finish. So go bin snitch, right? So here's the snitch. I'm gonna do list, and I'm gonna grab by CLI. There we go. So yeah, I wanted to have like a CLI parameters for the tile size and grid size, and I think this is precisely what I did in here. So I can remove that. So we also need to have a runtime parameter to limit the amount of threads, so I'm going to do that probably off screen. The runtime parameter to change the shaders, and a runtime parameter to change the colors. Okay, all of that looks fine. Remove the to-do about customizable tile and grid sizes, because it's done. Alright, and let's push that right into the repo. So maybe I need to refresh something in here, I'm not sure. So manage the renderer memory dynamically. Right. So how many changes did we make? It's a decent amount of changes, I would say. So all right, I guess that's it for today. There's nothing much for me to say. That's it for today. Thanks everyone who's watching me now. I really appreciate it. I hope today's stream was interesting. It was definitely interesting for me. It was really interesting to, you know, think about all of these things like buffer overflows and just trying to come up with proper numbers so buffer overflow will not happen. I probably made some mistakes in here. I don't claim that it's completely safe from this kind of buffer overflows because it's C, you know. But it was fun nonetheless. It was fun nonetheless. Makes you feel like a hacker man, you know. Makes you feel like a hacker man. All right, so have a good one, and I see you all next time. For the next streams, I actually prepared more interesting topics, so prepare for that. So. And yeah, check out the source code of the project. You can find the source code of the project in here. If you're watching on YouTube, check out the links in the description. And definitely, yeah, if you're on Twitch, check out the YouTube channel. So nothing much to say. Right, thanks everyone for watching. Love you all. Where is the... okay, here's the mic.